Okay. So last time we discussed about the determinant. Determinant turns out to be so it is going to give us a signed area or signed volume of the parallel pipe or parallelogram given by these vectors. And today we will turn to the section 1.8, and which is about the linear functions. And I'm going to give you the definition first. Okay, so this is the definition of linear functions. And well, if you remember, so then a couple of lectures ago, so we discussed what I meant by a function from Rn to R is a linear. A function was linear if so the function is respecting the vector addition and scalar multiplication. Same is true for this linear function. Well, today we are talking about the function from R, not Rn to R1, but we are talking about the function from Rn to Rk. So f is a function. So basically, f is a function which takes a n-dimensional vectors and whose output is another k-dimensional vectors. So this is a general linear functions, and the function is linear if the function is also respecting the scalar multiplication and the vector addition. So, okay. So, okay. Sorry. Okay. Okay. So, why do you even care about the linear function? The same reason as before. Well, because in general, evaluating a function value requires a lot of computation power and effort. But in case your function is linear, then you can actually, so technically you can compute the function values of every single vectors from your domain just by computing the function values at the basis vectors. So I mean, so the if f is linear, then the function value is completely determined by the basis vectors. So you know what I mean by these vectors? So E1 and E2, these are so-called the standard basis vectors, standard unit vectors. So I mean E1 is, the component of E1, for instance, like a component of E1, the first component is 1 and all the other component equals to 0. So this is the standard unit vectors. So this is, yeah, right. So last time, so I prefer to, we also describe a vector as a column vector. So these vectors. Because for any vector, for any n-dimensional vector, any typical n-dimensional vector will look like this. But this one can be written as a linear combinations of these standard unit vectors. So the function value of this vector can be written as f of this guy and since but because of the linearity of a function f, so this is f e1 and v2 of f e2 and vn of f en, right? Okay, so technically, so these, well, if you are able to compute each of these vectors, then the function value of f at the point vector v just reduces to the matter of addition and the multiplication. So well, so I mean, so everything turns out to be in the level of the elementary school algebra, right? Okay, so this is why the linear function is so important. All right. Okay, so let me just take a close look at this last expression. So, well, v1 to vn, these are definitely some numbers. They are real numbers. What about f of e1 to f of en? These are not numbers. These are actually k-dimensional vectors, right? Because this is the codomain of this function is in the Rk. So each of these guys are actually k-dimensional vectors. Well, we do not know the precise value of these vectors, but we can still give them names. So here, so I'm going to call them as, this guy is my M1, and this guy is M2, and this is Mn. And all these vectors from M1 to Mn, they are a k-dimensional vectors, right? So V1, M1, V2, M2, Vn, Mn. Okay. So therefore, if you can find out each of these vectors from M1 to Mn, then we can actually completely determine the function f. We know we have every information about the function f. So this theory can be summarized as a theorem 1.18, and it looks like this. Well, if your function from Rn to Rk is linear, then you must be able to find these vectors, M1 to Mn, and they are all k-dimensional vectors, so that the function value at this point turns out to be equals to this linear combination. Okay. All right. Okay. Okay. And today, we want to talk about the matrices, and these linear functions and matrices, they are very closely related. So, today I want to talk about the matrix, and why matrix is very closely related to the linear functions. You're gonna see it today. But before we do that, I want to talk about the matrix. Is there anyone who have never heard of the matrix? Well, I guess most of you have once in your lifetime heard about the matrix and their operations. But I realized that some of you are not 재수강생, so yeah. So for this reason, just give me a couple of minutes to give you a brief introduction about the matrix and their operations. Yeah. Okay, so in our textbook, so this is our definition of the matrix. So Okay, so M is called a K by N matrix. Well, if this guy has K rows and N columns, so basically matrix is a two-dimensional array of numbers. Well, I mean, so in some modern algebra, so in some modern mathematics, so entry of the entry of a matrix may not be the numbers, but for our purpose, we are talking about the two-dimensional array of numbers, real numbers. So this is our definition of the matrix. So typically, K by N matrix will look like this. So we have bunch of numbers, and they are arranged in this order. So, each of these are called a columns, and these are called the rows. So therefore, typically every entry of the matrix, it has two indices. The first index represents the row index, right? Because one. So this I represent on which row this entry is located. The second index, in this case, I denote it by J, is called the column index. So here, we have K rows and N columns. So this is a K by N matrix. Or sometimes, if I want to emphasize the I's row and J's column entry of the matrix M, then from time to time, I'm gonna use this notation. So this is the matrix. So this is matrix, and we have some operations on the matrices, just as we did on the vectors. Well, because on vectors we had the scalar multiplication and the vector addition, and same is true for the matrices. There are actually three operations. Well, first we have the addition and the scalar multiplication. Well, matrix addition is only defined for two matrices with the same indices. Well, so therefore, you can only add two matrices only if those two matrices have the same number of rows and same number of columns. Well, suppose that, okay, all right. So therefore, let me say M and N, they are two K by N matrices. I mean, they're matrices with same dimensions. And the matrix addition, M plus N is going to be another the K by N matrix such that, defined like this. I mean, so this is simply, you should understand it as a entry by entry addition. So, so I's row and J's column entry of M plus N is actually simply defined as this one plus that one. Okay. Okay, what about the scalar multiplication? Scalar multiplication, M is a matrix, and C is just a some number. And C times M is, C times M is going to be another K by N matrix. And I mean, so each entry of the matrix M is multiplied by the same number. So this is the scalar multiplication. Well, which is very much like to the vector addition and the scalar multiplication. All right, but now things are a little bit different. Then we wanna talk about the matrix multiplication. Remember, so we had in the world of vectors, so we were able to have the vector addition and the scalar multiplication, but there was no such thing as the vector multiplication. But in this case, in the world of the matrix, we have such a thing. If you want to suppose, this time, so M and N, their dimensions can be different. So say that the matrix M is K by S matrix, and N is S by M matrix. The point here is the number of columns of the first matrix and the number of rows of the second matrix, they must agree. Okay. Okay, so suppose that you have two such matrices, then you're gonna, M times M is gonna be K by M matrix such that defined like this. So, okay, so, if you have never heard about the matrix multiplication, this thing looks quite new to you, but this is, you may understand it as some sort of the dot product. So in this case, I's law and J's column of M times M is defined to be the I's law, this is the row index, and this is column index. Well, you first take the I's law of the first matrix, and you take the J's column of the second matrix. Now what? Then you are supposed to do something like the dot product. You remember dot product? Dot product is a component by component multiplication, and you add them all together. So in this case, I have 2 by 3 matrix, and I have 3 by 2 matrix. So, therefore, the first entry, the 1, 1 entry of this resulting matrix is going to be the dot product of this vector with that vector. So this is 1, this is -2, this is 0. So this is going to be -1. What about 1 and 2 entry of this resulting matrix? So this is going to be the dot product of this guy with this one. So this times this, 0, and this times this, which is 2, and this times this, which is -3. So 2 minus 3, so again, -1. And so for this entry, so dot product this guy with this, so, okay, so I'm not going to spend too much time repeating this. I mean, everything is just -1. So this is the resulting matrix. So this is how you're supposed to do the matrix multiplication. Okay, good. Before I move on, I want to introduce very important convention. As of now, whenever I was trying to describe a vector, then the vector was written as a n-tuple of numbers. So I draw the huge parentheses, and the parentheses, it has n slot, and each of these slots we had numbers. That was how I typically describe a vector. But another convention is from time to time, I want to describe a vector by using n by 1 matrix. So our convention n by 1 matrix is a n dimensional vector. So this is how we usually describe a vector. But this one is now identified to the V1 and V2, Vn. This is what? This is a n by 1 matrix. It has n rows and it has just one single column. So this guy, if your matrix has only one single column, then from time to time, so we call this guy as a column vector. And so our convention is, so we identify this vector as this column vector. So this is called a column vector. Okay. All right. So much for the the introduction of the matrix. Okay, now, okay, why we are suddenly interested in the matrix? Because every linear function, so this is very important slogan in the linear algebra. Every linear function can be represented by some matrix. Suppose that we have this function. Domain is from R. The domain is Rn, whose codomain is Rk, and suppose that this guy is linear. Then, because of the previous theorem, what was that? Yeah, because of the theorem 1.18, so V1, V2, Vn is hold on. Yeah. Okay. All right. Yeah. Sorry. Yeah, I don't want to spend too much time writing down this tedious lecture note. Yeah. So I prepared it last night. Yeah. Okay. Let's do this. Suppose that f is linear, then, well, the function value of f at this vector can be written like this. And what are these vectors from M1 to Mn? These are these guys can be understood as the function values of f at the standard unit vectors. Okay. And well, as I told you before, these vectors from M1 to Mn, they are actually k-dimensional vectors, right? And because of our convention, every k-dimensional vectors can be written as k by one column, right? So this is how I describe each of these vectors. So, well, this is my M1, this is my M2, and this is my Mn, right? And as you can see from this picture, each of these vectors has precisely k entries, right? Because they are k-dimensional vectors. Well, I do not know specific values of these numbers. I mean, these numbers may vary depending on the function f, but anyway, you must have these numbers. So yeah. So in terms of the matrix, well, so therefore I can write the function value of f at v can be written like that. Okay, great. Okay, now, and these vectors is now multiplied by these numbers. So v1 times m11, v1 times m21, v1 times mk1. So and so on, like this. And once you multiply each of these vectors by these scalar numbers, and you take a summation, then you're going to get this looking another k-dimensional vectors, right? And every entry of your resulting vector should be something like this. Okay. Right? Right? Okay. Yeah. I won't rush, so take enough time to look around and make sure that if my computation is correct. Okay. So this guy times this goes to here, and this guy times that goes to here, and this guy times this here, and this, and this guy times. Okay, good. Yeah, I'm good. I made no mistake. All right. Okay. Now this is the interesting part. This expression can be written as the matrix multiplication. M11, M12, M1n. This matrix by this column vector. Are you sure? Yeah. Let me try to find out. So, well, this one times this plus this one times that plus this one times this. It's going to be the first entry. which is precisely this one, right? And this one times this one times this, plus this one times that. And so once you take the summation of all these numbers, then you're gonna get this second entry. Likewise, this guy is this, then this guy times that, this guy times that, and you make a addition, then you're gonna get this number, right? So this, well, the point here is the function value of f at this arbitrary vector can be written as this matrix times another column vector, right? And okay, now I want to talk about the dimension of this matrix. So what is the dimension of this guy? It has k rows, right? 1, 2, 3, k, and it has n columns, right? So, sorry. Okay, so, okay, let me just cut to the point. If you can find all these vectors from M1 to Mn, and they are actually the function values of f at the standard unit vectors, then you're going to have n many k-dimensional vectors. And if you plug in each of these vectors to the column vectors of this matrix, well, if you list them in this order, this guy goes to here, and this guy goes to there, then this guy goes to there, then you're gonna get this k by m matrix. Once you have this k by m matrix, then computation of the function value at this point just reduces to the problem of the matrix multiplication, right? So from now on, so therefore, once you are able to find this k by n matrix, then computation of linear function is going to be turns out to be just tedious and very repetitive algebra. Isn't it great? I mean, so there is actually nothing to think of. Well, 되게 모든 것이 되게 기계적인 거기 계산 문제로 환원이 되는 거. 생각을 하지 않고 계산을 할 수가 있다는 게 되게 중요한 거예요. 왜냐면 그건 뭐지? 컴퓨터한테 시킬 수가 있다는 거죠. So this is why we are so interested in them. So I mean, and so being able to have such a nice k by n matrix is really good because, well, and the point is every linear function must have such a nice matrix. And this matrix is called the matrix representation of the linear function f. So this is called the matrix representation of f. Okay, all right. Do you think you can find such a nice matrix representation? Like, okay, yeah, this is so important. Yeah, so I want to spend enough time explaining this. Is it linear? No, this is not. This is a nonlinear function because, typically whenever you have the square function, then it's not a linear function. Okay, so yeah. And I believe this is a linear function. Well, just trust me, this is a linear function. Now, can you find the matrix representation of this linear function? Well, if you think you can, then just try it by yourself. But if you don't think if not, then okay, let me just find out. Well, since this is, well, okay, so let me just, before I try to find the matrix representation, just let me talk about the dimensions. The input vector is from the 2 dimensions, and the output vector is the 3 dimensions, right? So therefore, the resulting matrix, the matrix representation of this function must be 2 by 3. No, so sorry, 3 by 2 matrix, right? Okay. So 3 by 2 matrix. So it is going to have 6 entries. Okay. Now, what about these numbers? Can you find these numbers, these 6 entries? I mean, these are so easy because, well, if you have paid attention towards my lecture, then, well, it is not very hard to see that each of these columns consist of matrix F is nothing but the function values at the standard unit vectors, right? And well, and in R2, the standard unit vector is 1, 0, and 0, 1, right? So if I plug in 1, 0 here, then the function value is going to be 3, minus 2, and 1. 3, minus 2, and 1. What about the second? What about the second column of this matrix? The second column is determined by plugging in the second standard unit vector. And so it's going to be 1, 0, and 1. Okay. Right? Okay. The same question. Now, what if you want, okay. Can you find the function values at this point? Seven and minus 2. Well, the easiest and the quickest way is just going to be plug in x equals 7 and y equals -2 into this expression. Then you're good. But yeah, that is still good. But well, in the spirit of this lecture, what I want to do is I will try to multiply everything by this column vector. Then it's going to be 19. Sorry, my choice of numbers was not very good. But minus 14 and 9, I guess. Yeah. Aha. So this is how you're supposed to compute the function value. Are you good? Yeah. Okay, great. Great. So, okay, all right. So I want to end the discussion by introducing the theorem 1.19. And it goes like this. Every linear function from Rn to Rk can be written, well, or I prefer to say, can be represented in matrix by some k by n matrix. So we have, so this is a matrix representation of this linear function. And the function value at this point can be easily computed by using the matrix multiplication. This is clearly a column vector. Okay, good. Let me talk just a little bit more on the matrix. The identity matrix. what is an identity matrix? Identity matrix is a square matrix. In other words, a same number of rows and same number of rows equals to the number of columns. So this is what we call the square matrix. And what square matrix? Such that the ith row and jth column entry is either 1 or 0, depending on the columns and rows. So in other words, this is the identity matrix. So 1, 1, 1. And all these off diagonal entries equals to 0. So diagonal entry equals to 1 and all the other guys equals to 0. So this is the identity matrix. Okay. Why do we call this guy an identity? Because this guy plays the identity element in the matrix multiplication. And IN is called the identity matrix. Then for any n by k matrix, n identity matrix multiplying by identity matrix doesn't change anything, and so it has very nice property. And we also want to talk about the inverse matrix. MB and suppose that M is a square matrix, n by n matrix. And if there is another n by n matrix, and such that Mn equals to In and Nm equals to In, then we say M is invertible, and we usually call it M to the minus or M inverse. Or this guy is called the inverse of M. So this is the inverse matrix. So the point is, I need to point out some couple of important things. Well, I think the inverse matrix is only possible for a square matrix. So therefore, for non-square matrix, inverse matrix doesn't exist. This is very, very known fact. And even for the square matrix, there are some matrices that may not allow its inverse. In that case, we say the matrix is a singular matrix. Anyhow, so if my matrix is an invertible, a non-singular matrix, then, technically, but because of this definition says that in order to make sure that n is the inverse of m, then we will need to make sure that we will need to verify these two equations. But in fact, just verifying one of these two equations will suffice. If your matrix N satisfies one of these two equations, then actually that means your matrix N is the inverse of M. Well, I'm not going into the detail why that is true. Why that is true. So if you're interested, then I strongly recommend you to join the 응용선형대수 course. I mean, applied linear algebra. So 응용선형대수가 우리 제 생각에는 이제 포스텍 수학과에서 제공할 수 있는 가장 중요한 코스라고 생각하거든요. 그러니까 혹시라도 아직 거기 응선대 안 들으신 분이 있다면 꼭 들으시길 강력하게. 광고 시간, 광고. 애드 브레이크 광고 시간이었어요. 근데 꼭 들으셔야 돼요. 예. All right. Theorem 1.20. Okay, all right. So let me try to read this. I have matrix M, and which is a square matrix because, well, it is assumed that M is an n by n matrix. And U, V, W, they are the vectors in Rn. I mean, in this case, we are assuming that U, V, W, they are n by n column vector. A vertical, right? Okay, so, and this theorem is about to claim two statements. What about letter A? So, well, suppose that M times V equals to 0. So what does it mean? So this is n by n matrix, and this is n by 1 matrix. So, well, so dimension-wise, this whole thing on your left is an n by 1 matrix. So this is a n-dimensional vector. So let's suppose that this n-dimensional vector equals to 0 vector. Only for V equals to 0. So that means, well, so okay, let me suppose this. I have matrix M, and I multiply some mysterious vector V, and it turns out to be 0. But if that is true only for V equals to 0, so MV equals to 0 implies V equals to 0. So this is only possible for V is the 0 vector. Okay, let us suppose this. Then every vector W, for every n-dimensional vector W can be written as M times some other column vector U. Then writing down this column vector as the matrix times another column vector, this is possible. And letter B. Okay, this time around, so this is the converse of the previous statement. This time around, let us suppose that every vector can be written as M times some column vector U, n-dimensional column vector U. In this case, M times V equals to 0 vector implies V equals to 0. So, well, so therefore, letter B is precisely the opposite from the previous. Okay? I mean, converse of the previous vector, converse of the previous statement. So basically, so this theorem is about to say implies V equals to 0 if and only if for all W in Rn there is a vector such that W is MU. Okay. All right. So since this is an if and only if statement, so I will need to try the both sides of proof. Okay. So okay. Let me try to be truly honest. Yeah. if you are in the 응용선형대s course, applied linear algebra course, then this is probably definitely one of the most crucial statement in that course. But however, since we are working in the multivariable calculus, so the statement is this guy is not that useful. So I'm going to give you the quick proof of this. But don't worry about this. Don't worry about this. Don't worry about this too much. Okay. All right. So this is the proof for letter A. Well, okay. So this hypothesis says that MV equals to 0 only for V equals to 0. So this is my matrix M, and this is my vector V. So this is an n by n matrix, and this is n by 1 column vector. And we multiply this times this. So it's going to be like that. And and just as I did before, so I broke down each of these guys as something like this. Using the previous notation, and I'm going to call this column vectors M1, and this is M2, this is Mn. If you take a close look of this last expression, and we are assuming that this guy equals to 0. Well, and I hope you remember this. This last expression, for me, this one looks like the linear combinations of the vectors M1 from M1 to Mn equals to 0 vector, right? This last statement actually says this. So n times v equal to 0 means the column vectors of the matrix M, the linear combinations of the column vectors of M equals to 0, right? This is precisely the linear combinations of these column vectors, which is consisting the matrix M. And our hypothesis tells us that this is only possible for v equals to 0, right? I mean, in other words, this vector equation has only trivial solutions. Because in order to attain this equality, then v1 and v2 and vm, they must all equal to 0, right? So that means this reminds me of the definition of the linear independence. Okay. So that means each of these vectors are linearly independent. So, I mean, they are all n-dimensional vectors, and we have n such vectors, and these n-dimensional vectors are linearly independent. This reminds me of, in this case, we say these vectors are the basis vectors of Rn, and in that case, every vector, any random vector from Rn can be written in terms of the linear combinations of these basis vectors. So we already know that, but this last expression can be also written as W equals to M1, M2, and these column vectors times this column vector, right? So if you expand this, then this one can be also written as U1 times M1, U2 times M2, UN times Mn. So this last expression, written in terms of the matrix, can be written like this. And this is precisely W equals to M times some another column vector U. Okay. All right. All right. For the other side, for the other direction, in this time around, so we are assuming that every vector can be written as M times some column vector U. So for every vector W, there is another vector U such that W is M times U. Okay, so this is possible for every vector W. Therefore, let us replace this vector W by the standard unit vector EI. So this is standard unit vector EI. And for this vector, then I must be able to find another column vector u satisfying this guy equals to m times u. So this will u, I will name it as ui. So well, for this vector, I can find this vector ui such that ei equals to mui. And I is, well, and this relation is true for all such i's from 1 to n. So, in terms of the basis, can be written like column vectors. Sorry, in terms of the matrix. And this relation can be expressed like this. And, okay, so we have n such, matrix relations. What I want to do is this. So this guy equals to m times this. So, and if I put them in this order, this is E1, this is, just look at these column vectors. This is E1, this is E2, and this is En. And each of these vectors, each of these standard unit vectors can be written as m times U1, this is m times U1, this is m times U2, this is m times Un. So this, this can be written like this, but, if you can factorize this, I know this, there is some logic jump in this case, but, I hope you understand this, but you can somehow factorize this as the matrix m times these vectors, this matrix. What is this matrix? Because this is an n by n matrix, another n by n matrix, and every column of this matrix is actually these vectors, u1, u2, and un. And if you multiply this vector by that vector, then resulting matrix has columns that will look like this, and which is precisely this guy. And do you recognize this? This is actually the identity. Okay, so what is this? So this matrix times that matrix equals to the identity matrix. So that implies this matrix is actually the inverse of the matrix M. Right? So M is invertible matrix. Okay, good. Yeah. Now what I'm supposed to do is I need to prove that mv equals to 0 only for v equals to 0. Okay, now what I need to show is, suppose that this is true, then I will need to show that v must be 0. Okay. Okay. So now suppose m times v equals to the 0 vector. Then what I'm supposed to do is I multiply the inverse matrix of M to the both sides of these equations. But multiplying by any matrix by 0 vector is still going to be the 0 vector. And this is M inverse times M. This is the identity matrix. So this is V. So therefore, in this case, MV equal to 0 implies V equals to 0 vector. So proof is that. Okay, all right. Great. So much for the linear algebra. Okay, and turning to the last section of the chapter 1. Geometric applications in R2 and R3. Okay, so for now, so we studied a little bit of linear algebra, but we are not, you're not going to so deep into the linear algebra. So what we are interested in is the applications of all these linear algebras in the world of the 2 and 3 dimensions, because those two will be dimensions that we will be mainly interested in. Okay, and first, I want to describe I want to introduce some way to describe a lines or the planes in 2 and 3 dimensions. Okay, first we want to talk about the lines in 2 dimensions. Well, suppose we have two-dimensional vectors, and so these are set of vectors, right? So T is any real number. So X can be understood as some subset of vectors in R2. But I want to interpret this guy as a line. What line? Because, well, suppose that I do not have this guy. I do not have U. I mean, suppose that U equals the 0 vector. Then X equals to just the T times the vector V. And what is this? It is actually the span of the vector, a one-dimensional subspace spanned by the vector V, right? So in other words, I want you to imagine that this is a two-dimensional plane, and this is the vector V. Then T times V is going to be a one-dimensional line passing through the origin, right? Now, this guy has been now parallelly translated by U. So therefore, if this is U, then this is going to be TV plus U, right? So in other words, we can say this expression represents a line passing through may or may not through origin, but what I'm sure is that this line must pass through the point U, and is parallel to the vector V. Okay, so this is a line. And same is true for 3 dimensions. So again, this is a 3-dimensional line in 3 dimensions, which passes through the point U and parallel to vector V. Okay. 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 Now we want to talk about the 2-dimensional plane embedded in the 3 dimensions. Suppose that we have three 3-dimensional vectors. And I want you to consider this. S times V plus T times W. And S and T there, just real numbers. What is the geometric interpretation of this expression? Just like before, so let me just ignore this vector U first. So let me say that U is the 0 vector. Then, in that case, X is going to represent a 2-dimensional plane spanned by vector V and vector W, right? So, I mean, you can easily imagine a 2-dimensional plane in R3, which is passing through the origin, and which is containing the vector V and W at the same time. So this is the two-dimensional plane that I'm talking about. But since we have this additional vector U over there, so therefore this is going to represent a two-dimensional plane. So this is going to represent a two-dimensional plane, which is parallel to the span of VW, but parallelly translated by vector u. Okay. So this is a plane. Okay. Right. And well, in terms of the coordinate, so I can say like this. If so, we give these vectors a coordinate u1, u2, u3, and v is v1 and v2 and v3, and w is w1 and w2 and w3. Okay, so u plus sv plus tw is going to be this guy plus s times this plus t times that. So u1 plus sv1 plus tw1, u2 plus sv2 plus tw2, and u3 plus sv3 plus tw3. And this guy equals to x, and x, yeah, well, this is the vector x. It has three coordinates: x coordinate, and y coordinate, and z coordinate. So, speaking of coordinate, the x coordinate and y coordinate and z coordinate, they're going to be, so this is the x coordinate, this is the y coordinate, and this is the z coordinate. Okay, so this is how we describe the any general two-dimensional plane. So this is, or sometimes we call this expression as the parametric description of the two-dimensional plane in R2. Parametric description, I mean by, so we have 2 degrees of freedoms. Well, so S and T, so you're free to choose any number you like. But whenever you choose any number for S and T, if S and T they are fixed, then it's going to give us some X, Y, and Z coordinate. And all these coordinates and all such point will be the member of the plane that we are talking about. Okay, so this is our parametric description. Well, this is one way of describing a plane in R3, or there is another way to describe a plane by using a point and a normal vector. What do I mean by that? So, well, there are 2 different ways to describe a two-dimensional plane in R3. The first one is once we describe 2 vectors v and w, and parallel translate the plane by u. So this is what we did here. And the another way to describe a plane is by describing a normal vector. Because whenever you have plane in R2, whenever you have the plane in R3, then that plane must be normal to some direction, right? This is what we call the normal vector. And so once you have the normal vector, then that is going to give you some sort of plane which is passing through the origin. And if you parallel translate the vector by u much, then that is going to give you another way to describe a plane. So it goes like this. Well, okay, so this is the three-dimensional space. This is x, y, and z. And well, and I want to describe this plane. Well, say that I am not sure, so which vector, so I'm not sure which vector this plane is containing, but say that I know its normal direction of this plane. So this is the normal direction. And suppose that I also know the one point of the plane that this guy is passing through. So U is a point, just choose any point you want in the plane. And N is the normal direction of the plane. Yeah, well, in terms of coordinate, so let's say that this is N1, N2, and N3, and U is U1, U2, and U3. Okay, now just choose any random point in the plane, which I will call X. If X, Y, Z is a point in the plane, then this is very interesting observation. Why? Well, okay, what is X minus U? This is X and this is U. Therefore, X minus U must be this vector. This green vector should be understood as X minus U. Well, this is not precise X minus U, but this is parallel to the X minus U. Okay, now, and as you can see from this picture, X is the point in the plane, and U is also a point in the plane. Therefore, this vector X minus U clearly is contained in the plane. And since N is supposedly a normal vector, normal direction of this plane, therefore, they must form a right angle. This is why the dot product of N and X minus U must be 0. So in terms of the coordinate, N1, N2, N3, this is the vector N, and dot product with X minus U1 and Y minus U2 and Z minus U3 equals to 0. So N1, X minus U1 plus N2, Y minus U2 plus N3, Z minus U3 equals to 0. Well, okay, I just ended up a single equation, single liner. And I claim that this equation is also representing the plane, which is normal, which is normal to this vector U and passing through the vector U. So which is normal to vector N and passing through the vector U. Is given by this single equation, one liner. So in other words, so every X, Y, and Z satisfying this relation must be the point in this plane. Why? Why is that? Because, well, in terms of the algebra, yeah, I can describe like this. Well, the solution of this equation, solution x, y, and z of this equation is the point in the plane. In other words, well, originally, so you can understand, you can understand this equation as some sort of restriction imposed to the free variables x, y, and z. Without this restriction, the degree of freedom was 3, right? Because we have 3 variables. So 3 dimensions, but imposing one restriction, so that is going to decrease the degree of freedom by 1. So, well, because in other words, if you do not have any restriction at all, then x, y, z can lie freely in R3 space. But since we were imposing one restriction, that is going to give us, well, get rid of one dimension. Therefore, a single equation imposed to x, y, and z may usually refers to a 2-dimensional surface in R3. Well, but here, since this equation is linear equation, therefore it is representing a flat plane in R3. But, well, if this relation is not linear, suppose that this relation is a quadratic or a quartic relation on x, y, and z, x, y, and z, then that is going to give us very interesting picture surface embedded in R3. Okay. Lastly, let us compare this with this. This is actually this is going to give us more explicit a coordinate of x, y, and z, right? Because whenever you plug in x, and t, then it is going to give you x and y, z coordinate of the plane. But, well, on the other hand, you'll need 3 different equations. Well, however, this equation you're going to need just one single line. And this actually gives the same information just as we did in the parametric description. But however, if you want to find out x, y, and z coordinate from this equation, then you will need to solve some relation. You're going to do just a little bit of algebra. Yeah, so these are the pros and cons of these 2 descriptions. Okay, so this is for today, and I will see you next time.